4, 3, 2, 1, top. Allumage Vulcain. Allumage EAP.
The chemistry of rockets is really all about the chemistry of combustion. And these demonstrations involving methane are a great place to start explaining combustion reactions. Schools almost always have a supply of methane gas in their labs. And people sometimes wonder, what would happen if I lit the gas that comes straight out of the gas tap? Will it go back down the tube and will it blow up the lab? Will it even blow up the whole school? Well, the answer is no, it doesn't. And I'm going to show you why. Now, we don't have a methane supply here, so we're having to use this cylinder here, but it does have a gas tap. I'm going to first of all protect the floor in this case, but what would usually be the lab bench. I'm going to light my spill, get it ready to go. And when I've got it alight, I'm going to turn on the gas tap. And I'm going to light the gas. Immediately it comes out of the tap. Here we go. Now, it's quite spectacular, but it certainly hasn't caused an explosion. And in fact, you can probably see that there's a gap here. There's a gap between the tap and the flame. And that's because the methane gas has to mix with the oxygen before it can react. It's not methane that combusts, it's methane and oxygen. In fact, what we've got here is our fire triangle in action. We've got a heat source, the fuel, and the oxygen combined. If I reduce the pressure, you'll be able to see the size of this gap reduce a bit. I can get it to travel right back to the tap, but because there's no oxygen here, there's still no explosion. The methane can only react once it's got outside and reacted with the oxygen supply. This next demonstration, I'm going to connect the methane supply to a rubber tube. This is exactly the same sort of tubing as you would use with a Bunsen burner, but there's no Bunsen burner on the end. Instead, the methane is going to bubble into this tray of water. And into the water, I'm just putting a squirt or two of washing up liquid so that I get lots of nice bubbles. And I'm going to produce a whole tray full of methane bubbles. Here we go. Each of these bubbles is trapped methane. I'm moving my hose around just to generate lots of nice bubbles. Methane is slightly lighter than air, and so the bubbles are sitting up nicely on the surface of the water. And I should think I've got about plenty now, so I'm going to turn off the gas tap. Stand back, light the match, and drop it in for a methane bubbles explosion. We're going to do that demonstration again, but this time on the hands of a willing volunteer. So, while I make lots of bubbles here, would you like to get your hands nice and wet? Get the palms wet and the back of the hands wet, just as a precaution. Now, we're getting to make plenty of bubbles here, and I'm going to try and pile them up all in one place. And when we've got enough bubbles, I'm going to get you to put your hands into the water, scoop up the bubbles, try and open up your fingers a little bit and let the water through. Scrape your hands, the back of your hands on the tray so that you don't have any bubbles underneath your hands. So hands into the water, scoop up lots of bubbles, scrape off on the back, make sure there are no bubbles underneath. Okay? Now hold your hands out. Keep your hands out nice and far away from you. What you don't want to do is go like this when they light. So, here comes the match. And she's survived. Molecular models are a really good way to introduce students not just to chemical formulae, but also balanced chemical reactions. Here, the black represents carbon and the white represents hydrogen. So this is a methane molecule, CH4. It reacts with oxygen, and here are two oxygen atoms joined together to form an oxygen molecule. Oxygen is red. And those two react together, as we've seen, to make carbon dioxide and water, CO2 and H2O. And the formulae are really clear when you see the models. You can't help but understand, I hope. But you should probably also be able to see that this equation doesn't look right. we've got more hydrogen over this side than we have in our products. How could I make just one water when I had 4 hydrogens in my methane molecule over here? So I can balance up my equation by adding another water molecule. I've now got 2 H2O. And if I do that, I'll now also need to add another oxygen, 2 O2. A really good introduction to balancing chemical equations. We've been focusing here on the combustion of methane. Now, although methane isn't used much as a rocket fuel, it's combustion that's at the heart of every rocket system, like Ariane or Vega. Every rocket requires both a fuel and an oxidizer.